Hi, I'm Ben-Yaakov. The title of this presentation is Hard and Soft Switching in PWM Converters. Let's start off with the notion of hard switching and see what's bad about this mode of operation. As an example, I'm showing here a boost converter, which consists of a switcher, this is a MOSFET transistor, a series inductor, a diode, and an output section, which includes a R sub O represent the load. Now, the way this converter works is that the transistor turns on and off, shorting this point, and then the inductor is actually pumping in current to the output. Now, let's have a look what happens when the gate is turned on and off. During the turn-on transition, which is here, the current of the transistor, this transistor, is starting to rise. There is a delay, and also the rate of rise, the rise time, could be rather slow depending on the type of transistor and also on the parasitic elements that you might have. For example, inductance of the wire, capacitance at the input, all these which sort of delay the turn on of the current. So the current goes up, and then transistor is on. We see here the current of the inductor, which is building up, and then during the turn off transition, the current starts to go down again. There is some delay, and there is a certain rate at which the current goes down. This is again because of the fact that you can't turn the gate, the internal part of the gate, very quickly, and therefore the current has some delay and a certain rate of change, which is not at zero time. While the current is going up and down, of course, the voltage across the transistor, that is this voltage here, will start from the high voltage. This will be actually the output voltage, which we see when the transistor is turned off, and then the voltage will go down as the transistor starts to conduct. Now again, this drop is not immediate, takes some time, there is some delay, I'm going to talk about it in a second, and consequently, what we have here, we have sort of an overlap of the voltage going down, the current going up, and this product of current times voltage implies power, and this is in fact a power which is lost. These are losses, power dissipated, and causing, of course, or reducing the efficiency of the circuit. Now, since this happens every transition, then this will be dependent on the frequency. The higher the switching frequency, the higher the losses, which sort of limits the high frequency or the highest frequency you can operate in a efficient way. The same thing actually happens at the turn off. This is the turn off. Again, we have an overlap. This is power loss, and these losses will increase as the frequency goes up. Now, we would like to work at high frequency because then the size of the inductor and capacitor are going down, and this is, of course, very desirable. And these switching losses are actually limiting our ability to go to a high frequency. Associated with this problem is the fact that the diode, this is this diode here, is imperfect. Typically, in a practical diode, if you start with a forward current, this is the current through the diode, and I'm showing it here, and then as the transistor here, this transistor, is shorting out this point, we are actually imposing a reverse voltage on the diode. Now, you assume maybe that as the voltage reverses, the current will stop, but it does not. In fact, what happens is that the residual current of the leakage inductance, and there is no escape. Each branch will have some leakage inductance. This residual current is sort of going down because of the polarity of the voltage now. It'll reach zero, and in fact will go negative. This is called the reverse recovery of the diode. Now, the reason for the negative current, which sort of looks maybe strange first, is because as long as you have charge carriers at the junction, the diode is conducting both ways. So until the charges are swept off the junction, the diode is conducting, and then eventually there'll be no charge in the junction and it'll snap back to zero. So this will be a sort of a peak reverse current, and this change or this interruption or this stoppage of the current will cause a high voltage, because we know that V is L the I dt, and if the I dt, that is the rate of change of the current, is fast, like here, then you'll generate a high voltage. Now, this high voltage, in association with the capacitance of the diode and other stray capacitance of the circuit, will cause oscillation. So, consequently, what you'll see is that as the voltage goes down, you'll see some sort of a interference here, oscillation, as well as you'll see some oscillations here. And this is, of course, increasing the noise and causing radio frequency interferences, which is highly undesirable. Now, another problem is that as long as the diode is conducting, that is, even in this region, the voltage across it is low, so that as the transistor is turning on, the diode is sort of shorting out the output to the transistor, and again increasing the losses. So all these are problems of hard switching, and soft switching is intended to remedy some of these problems. Now, what do we mean by soft switching? The idea is basically sort of to shift the rate of changes here of the current, or the slopes of the current and the voltages across the transistor, such that they will not overlap, or at least there be a minimum overlapping. Shown here is an ideal case. If I can turn the transistor, or we can operate the transistor in such a way that the voltage across it will drop before the current goes up, there'll be no overlap at all. This is a true zero voltage switching. And of course, the switching losses will be here very low. A compromise is the pseudo soft switching, in which we really don't separate the two, but rather we slow down one of them, in this case the voltage, so that there's only a minimum overlapping. So this will be called a zero voltage switching. And if we do the same thing with the zero current switching, here we turn off the current before the voltage goes up, and here we slow down the rate of rise of the current so that the overlapping is minimal. So there are possibility of zero voltage switching, zero current switching, and each could be either true or pseudo. Now, for a true zero voltage switching, either this or this, you need some extra circuit. The reason is, let's have a look in here. If you want the voltage to drop before the current goes up, Now the current goes up because you have this gate voltage, signal, control signal coming to the gate. So you have to do something before this happens in order to cause this effect of the voltage going down. Now obviously the circuit itself couldn't do this because it doesn't know that there's something going to happen here and sort of foresee it. So you need an extra circuit that will sort of do the lowering of the voltage before this gate voltage goes up. Same thing goes for the zero current switching. Now for the pseudo current or voltage switching, we can actually use the circuit itself with some extra components. So in general, we can talk about three types of snubbers. These snubbers are actually, it's a definition, the definition of which will be sort of to slow down or reduce the rate of changes. We can talk about the lossy snubber, and this will be a circuitry that will cause a change in the rate. This will be a circuitry that will cause a change in the rate of rise or fall of the voltage or current, but using lossy or dissipative components like a resistor. So in this case, we might reduce the switching losses, but at the expense of losing some power in these extra components. We can use passive lossless snubber. These are additional circuitry that will again slow down the rate of rise or fall with components which are basically LNC, which are reactive and ideally non-dissipative, and this will be a lossless snubber. And of course, we can have an active lossless snubber. These are the extra circuitry. There must be some sort of perhaps an extra transistor or an external transistor that will cause the effect of true soft switching. I'm going to show you a sample of each of these. Let's start with the lossy snubber, and I'm going to demonstrate it on a diode snubber. Now, what is the problem of the diode? As I've just said, because of the reverse current, the interruption of the current of the leakage inductance is going to be here oscillation due to the stray capacitance of the diode and some other capacitor of the circuit, which could cause very high voltage and in fact cause a breakdown of the diode. So what can we do? Well, here is shown a RC snubber in which we have a resistor and a capacitor, and the idea is that as we have this current flowing and the diode stop conducting, that is here, the current has now a new path to go. And in fact, what will happen is that the energy of this stored in the stray inductance will sort of move to the capacitor, which will be charged in this direction. Notice that this direction means that there is a reverse voltage on the diode. This is extra to the outside reverse voltage, so that we have now a diode which has an extra reverse voltage stress. So one has to be very careful not to generate too high voltages from this capacitor. Now, once the circuit is switching to the other state, current will start flowing this direction, the diode will conduct, and consequently the RC circuit has now a path to discharge this way, and get back to the zero condition. So the basic concept of designing this R snubber is very simple. First of all, we equate the two energies, energy stored in the inductor to the energy eventually passing through the capacitor, I square L over 2, V square C over 2, from which we can get an estimate of the capacitance that we need. Of course, we have to decide on the maximum voltage that we allow. A problem is to know what is the stray inductance. This is not trivial, and in most cases we do some sort of a trial and error. We start with a large capacitor and then we reduce it until we get to a V that we like to have. By the way, the larger capacitor, the more power will be dissipated, because the energy of this stored in the capacitor is eventually dissipated in this resistor. So with a large capacitor, we are going to dissipate a lot of power so that the resistor will get hot. So we are losing power here. Maybe we are protecting the diode, but we are losing power in the circuit. Another constraint is that RC, that is the time constant, should be smaller than T on. This is the time that we have when the diode is conducting and we have a discharge of the capacitor. So this will be an example of a lossy diode snubber. I'm moving on now to a passive lossless snubber. I'm going to show you a zero voltage switching snubber at turn off. I'll explain what it means. And let me just first of all talk about the concept, and then I'll show you how the circuit is actually built. So we are talking about snubbing at turn off. This is the gate voltage. It's going down. Drain current goes down. The drain voltage VDS is going up, and we are going to slow down the rate of rise here so as to minimize this overlap. The concept is to add sort of a capacitor here. So as the transistor is turned off, this current is charging the capacitor, and the rate of rise of the voltage is I over C. So the larger the C, the slower will be the slope here. However, this circuit is kind of dangerous because, well, it's fine when we turn off the transistor, but when we'll turn it on again, this whole energy will be dumped into the transistor. So this is not a practical solution. This is just a concept, what we are going to do. What we'll have to do is during the turn on, so to separate this circuit and in some way discharge the capacitor through another path. And this is exactly what this snubber is doing. And this snubber was suggested by Moshe Dumb, Richard Riedel, and Nathan Sokal in 1982. Credit is to them. And this is the basic circuit. I'm showing here a circuit, or the snubber, around a boost converter. The boost is this inductor, the diode, the transistor, the output section. And the snubber is this part here. Consists of two diodes, an inductor, plus a capacitor. To understand the operation of the diode, we'll start with, indeed, the point of turn off. That is, the transistor was conducting. This point was actually grounded. Now the transistor is turned off. This is the gate voltage. It's turned off. Transistor stops to conduct. And the current that was going through this transistor is now interrupted. There is no current here. Now, the transistor itself has some self-capacitance, CDS, depending on the size of the transistor. But now we have an extra capacitor, which is this capacitor here. Now, as it turns out, the initial conditions of this capacitor voltage are such that it has a polarity of this nature, and the magnitude is Vin. So, at the beginning, the voltage here, when I sum up this voltage plus Vin, is 0, as it should be, because the transistor is shorting. Now I'm releasing the transistor. So the current now is flowing this way and into the capacitor. So the total capacitance will determine the rate of rise. This is the current. I over C is dV dt. This will go on until the voltage here at this point reaches this point, which is the output voltage, which is here. The diode will start to conduct. And then we end up with this situation. I'm showing here, I'm not showing the transistor because it's off. Showing here the charge of this capacitor. Well, I might add here this thing, but at the end, the capacitor is fully charged to the voltage between this point, which is, here is V out, and here is V in, so the capacitor will be charged this direction. V out is higher than V in, to this magnitude. And this is during the off time. Off time in terms of the transistor. Transistor is off, current is flowing through the inductor and diode, and consequently we are in the off state, powering state. Now we're coming to turn on. Turn on means that the transistor starts to conduct, and I'm showing here that we have here a short. When we have here a short, this capacitor is charged. There is an inductor here, snubbing inductor, a diode, and consequently we have here a resonant circuit which is generating a sinusoidal wave, and the capacitor is starting with a certain voltage, minus plus here. Voltage will in fact reverse, and as it goes up and up, becoming more positive, this is ground here, and it will become here positive. It will eventually reach the level of this point, which is V in, and it will clamp to it. I'm showing it here. Now, at this point, the inductor may have some current through it, which will go this way, and because the voltage is of this polarity, the current will sort of go down and eventually reach 0. So what we did with this thing here is in fact discharging this capacitor back. Now, since this is ground, the capacitor is clamped to this point, then the voltage is V in. So we end up with this situation. This is exactly what we started in here. So next time, as the transistor is turned off, we have this current. I'm sorry, there is here a mistake. That is not here. Here is the diode. The current goes in here, and again we'll have a slow rise time here of the slope. So this is a very nice circuit. It has been used in numerous designs. There are some limitations here, which I'm not going into. One of them is that this circuit will operate only if V in is larger than half of V out, for the reason that otherwise we are not going to get back to this clamped voltage. Now let's move forward to demonstrate an active lossless snubber, and I'm going to show it on a bridge type converter, which is called phase shift PWM converter. Basically, we have 4 transistors here, which are feeding a transformer, which has a rectifier, the output, and of course this is the output section. In a regular bridge circuit, we would operate Q4, say, and Q2, generate this voltage. Then there'll be some sort of off time, and we will move to Q1 and Q3. So we'll generate a voltage of this kind. Therefore, we are going to have between these points here a square wave, which is then rectified here, fed to this filter section, you might say, and generating V out. This will be the regular bridge, which is hard switched and has all these drawbacks that I have mentioned. Now, the idea of the phase shift PWM converter is that we are trying to do this transition in a soft way, soft switching. There's an extra inductor here, which is usually put in, or you can have it in a proper design of a transformer to be part of the design, which is important for the operation of the soft switching, as I'll show in a minute. So let's see how this thing works. Let me start with the powering stage. That is, this transistor is on, this transistor is on, so we have plus here, minus here, this diode is on, and power is moving toward the output. This power is fed to the output. Now, contrary to the case of the hard switched, we are not turning off the 2 transistors. What we are doing here, in fact, we are turning off this transistor only, leaving both this transistor and this transistor in the off stage. This is the only transistor which is on. Now what will happen here is that since we have current stored in this inductor, energy stored in this inductor, this current will flow in here and start to feed this point, and the voltage will go up, the rate of which depends on the current and the total capacitance that we have here. This could be the internal capacitance of the transistor themselves, or we can actually add some extra capacitance here if we like to have this rate even slower. So what happens is that this voltage goes up and up and up, and eventually it'll hit the point that the diode will conduct. So we actually cause by this inductor a self-commutation and bringing up this voltage back to here. Now we can turn on the transistor. Now we are turning it on at 0 voltage, because prior to turning it on, the voltage here was just the voltage of the diode, which is very small, it's almost 0, not 1 volt, say. And as we turn on the transistor, this is a true 0 voltage switching. So what we did, we lowered the voltage on the transistor, and only then we turn it on. So we turn on this, and we are now in a state that current is sort of circulating this way. So there is a zero voltage here eventually. So we are like in the off state. There is no power going to the output. And then we are ready to go to the stage where eventually Q4 and Q2 will conduct. But again, we are doing it in stages. We'll first, showing it here, first turn off Q1. So only Q4 is conducting. Again, this current, which is flowing this way, will charge this capacitance, and excuse me, the current goes the other way. I'm sorry. This was the way, I mean, it was plus here and minus here, so the current was going this way. So this is the direction of the current. So eventually this diode will start to conduct, and then we are ready, when this diode to conduct, to turn on this transistor under zero voltage switching. So as you can see, this circuit is very clever in that it uses the transistors of the bridge itself to commutate the voltage, and therefore reduce the voltage on a transistor, say this one, before we turn it on. So it is a true zero voltage switching in this case. The current shape of the converter, this would be like the current in, say, in here, would typically be, this is the commutation period, this is the current actually reflected back from the inductor, the output inductor. I mean, the current goes this way, but we are sort of looking at it from here. And here is again commutation. This brings me to the last point here to see what type of excitation do we need for the transistors, the signal, in order to accomplish what we want. So let's start with the situation that Q1 and Q4 are conducting. Here they are conducting, and this is conducting, Q1 and Q4. Next thing we want to do, we like to turn off Q4. Here I am turning it off. And after a while, as this voltage goes up, the diode is clamping, I like to turn on Q3. Here is Q2. All this time Q1 is on. At a given point, I'm turning off Q1, releasing this point to go down. So here's Q down. And after a while, I'm turning on Q2. So this is Q2. So as you can see, these are sort of funny looking waveforms. And as you can see, that there's some shift of this signal, and this is why it's called phase shifted PWM converter. Now there are chips, of course, control chips that will generate automatically this waveform. You don't have to worry too much about it. You just have to choose the proper IC controller to do the job. This brings me to the end of this presentation. I hope you enjoyed it and you'll find it useful. Thank you.